Okay, so for today, my screen is visible to everybody. Uh, is my screen visible?
Yes, sir.
Okay, okay, fine. So our today's topic is on steady state thermal analysis. So before going on to that, I just want to recollect like what we have seen until now. So in first session, it was a totally like a theoretical one, including some 1D or I will say 1D element analysis. Basically, some beams were there. That was our first session. Then in second session, we solved some 3D elements. So we have solved some problems which was having 3D geometries. Uh, Afterwards, we have seen like combined calculations of like buckling analysis and static structural analysis. And as today we have seen model analysis, and again we have seen pre-stressed model analysis into that. Today, we will be having look into the little bit different topic. So not exactly related to a static structural, not exactly I'll say stresses and strains and all that. But now I will be talking about thermal stresses now, or thermal expansion, or maybe heat flow. Like now I will be talking in terms of thermal terminologies instead of my structural terminologies. Fine. So here, maybe we will quickly go through some of the theory portion of it. So maybe if you just go on to Google and if you type steady state thermal analysis ANSYS, you can simply get this PDF available. So I simply took it from Google. So, just to know the base or maybe the concept behind this calculation. So, I'll just go to, so this is the our project window, like workbench project window. So now we will be dealing with this analysis system, which is steady state thermal system. Right now, instead of like as we said, we drag and drop static structural, we drag and drop like buckling one, linear buckling or eigenvalue buckling. Now we have to start with steady state thermal. Here again, same formula. So this is nothing but relation between my heat transfer or heat transfer coefficient and my temperature, right? So this equation basically will be solving in the background. So here the symbol like this one means it will be in matrix form. So maybe in upcoming years, or maybe in third year, or maybe in last year, you will be having the subject, or I don't know, maybe in third year itself you have the subject of numerical methods. In that maybe you will solve such problems analytically also, means you just put maybe 3 by 3 4 by 4 matrix and you solve it on paper. So this we can also try. So same thing, as I told, like we will be solving 3 by 3 or 4 by 4 matrix. But if I'm having like a matrix size of around 1000 by 1000 or 2000 by 2000, that's why we are now here. So that's not possible to solve by hand calculation. So we need such softwares to calculate for us. Again, there are some assumptions. You can go into that afterwards. Maybe I'll simply scroll through all this. So here again, same thing. We can have calculations for solid, surface, and line bodies. Basically, 3D, 2D, and 1D bodies. Fine. uh, Here, materials what we defined for our structural calculations. The only difference between that material and this one is here the isotropic thermal conductivity. that part is additional. So it wasn't used during my structural calculations, even if it was present over there. But now in this thermal calculation, uh, this value is very important. Again, we have this isotropic thermal conductivity value, maybe constant at some temperature, or maybe you can just enter this value in the form of table. Maybe for minus 100 degrees Celsius, what is my thermal conductivity? Right, for 0 degrees Celsius, I'm having some thermal conductivity. At 100, I'm having some. At 200, I'm having some. Means I can give input as a graphical data. So this is nothing but my material property, right? Uh, Again, I'll skip this contact part. This is also related to contact. Okay, now, so these are the boundary conditions which will now we will be using. So in static structural, we saw boundary conditions like force or like pressure or like a fixed support, right? So those type of boundary conditions we saw over there. But here, in case of thermal calculations, we will come we will see about heat flux or heat flow or maybe internal heat generation, sometimes temperature. So these will be our boundary conditions for these thermal calculations. So you can see over here convection, heat flow, temperature. Like these will be our boundary conditions for the calculation. So here we have. So can anybody tell me what is this equation? Uh, Anyway, it has written over here. It's just the equation of convection. So H is nothing but my heat transfer coefficient or coefficient of heat transfer. A is my area, and the T surface and T ambient. So this is nothing but my equation of convection. Similarly, I have one for conduction, and I also have for radiation. So this is for my radiation case. Fine. So same will be used in our calculations. And yeah, again, what input parameters you need to know for calculations. So very important is this film coefficient. So nothing but this value. Uh, One very interesting story actually I need to share with you during my masters when I come across the subject of heat transfer. Then actually one of my professor told in the class. So what do you think about this symbol H, or what do you think about this terminology? So coefficient of heat transfer. Then he said there are hundreds of PhD theses are available on only this one letter H or only this one terminology, coefficient of heat transfer. And still there are lot things are there which are need to be found out. So that's why this is very important to look your direction should be like this. Means you should know how like how it is behaving basically. Means it is not only related to our problem solving. Maybe if I'm having such a model, and if I'm having some temperature over here, so you should think. Means how my results will be, or how my results will be calculated. So which formula it will use, and basically what input parameters it will use. So that should be in your mind whenever you will be calculating such thermal cases. So it will give you like more confidence on your results basically. Hmm. Again, these are on nothing but only uh, input parameters. Basically, I'm selecting over here only stagnant air type of stagnant air, maybe horizontal, vertical, or maybe any simplified case. So I have like the data, inbuilt data for this. So instead of defining this value like film coefficient, I can define it by using any such a standard method. Uh, so this is for radiation. Again, same things. I can define whatever I'm having as standard, or I can simply give them as input. Okay. One more thing. So yesterday we have seen like we can have pre-stressed model calculations. So here also same things, because in steady state thermal analysis, I will have results only in terms of my thermal terminologies, not in terms of my structural terminologies. So if I need to get results in the form of stresses or maybe deflection, then what I need to do, I need to take these thermal results as an input for solving my structural problem. In this case only I will get equivalent stress or maybe deflection. Here I will only get my temperature profile or maybe my heat flux. So only thermal results I will get from this steady state thermal tank. Okay. So we will be seeing this today in your assignment problems. So here are some examples. So I'll skip them. Okay, fine. So that's it, I guess. So just for like a rough idea regarding what thermal calculations are and how we are going to do that. So maybe I'll simply do one thing. I will close this. I don't want to save this. Maybe yes, I'll go to the workbench. So just go into the start menu, simply type workbench. Before going to that, I just want to ask one question. Like anybody of you have installed Ansys successfully, means without any license error or something, or still nobody has succeeded to install Ansys? Okay, nice, very good, Praveen. So you can try all the assignments by yourself. And one more thing, have you received like 3D models from Ajay? Okay, perfect. So yeah, you can practice, and like if you come across any doubt, so please ask those doubts, because when you try by yourself, you will come across many doubts. I'm pretty sure that you will come across some queries. So you just simply write it down, and you can ask me in our sessions. So there is nothing to worry, right? You can ask me any doubts, like maybe related to session one, session two, or maybe anything. Okay, so fine. So now I have just opened like a project window. First of all, I'll save it. So maybe assignment number 6. So session 6. So before going to that, I'll just read out the problem statement for our first problem. We have to calculate this geometry, which will be having structural steel thermal category material. Element size will be 3 millimeters. Temperature on top face should be 2000 degrees Celsius, and convection on all faces except the top one. Convection coefficient value they have defined as zero point 0.2 watt per millimeter square per degree Celsius. And output should be temperature distribution and heat flux. So these are my outputs. So can anybody tell me what this component is? Maybe I would have told during when I showed you the model earlier. Can anybody tell me what is this component? By seeing onto just this 3D part and seeing onto this boundary condition. So here we will be having 2000 degrees Celsius. Can you correlate this to any real world case? So what is this model basically? Can anybody guess? So which is this part? What? Okay, great, great. So this is exactly a piston in the IC engine, and in IC engine only we will reach such temperatures, so around 2000 degrees Celsius, around 3000 degrees Celsius, and this is exactly practical problem. So these are the practical. This is the practical case. Okay. So this is nothing but one of the piston from IC engine, and here the grooves they are basically for my rings. So just to do not let my gasoline or maybe my whatever fuel to go into the crank gear side, so or my gearbox side, right? Okay, now I'll just go here and just double. So here we have three thermal cases. So steady state thermal we will use. Fine. I'll write as problem number one. So fine. What I will do now, I'll check the materials. So whenever you are selecting, maybe I'll go back to the project window. Whenever you are selecting this steady state thermal, it by default it takes material data for thermal thermal calculations. Maybe I can show you the difference between both. I'll simply drag and drop one static structural over here, and maybe I'll click on the engineering data. So same material I'm having, structural steel. Just observe the material data available over here. So what material data I need, or I must have, so that to calculate this static structural problem. First is density, right? And here second is my Poisson's ratio and Young's modulus. So these properties are must. So check the properties what are there in case of static structure. And now I'm going into my thermal material. So I'm having same material as a structural steel, but see my properties. They have defined only isotropic thermal conductivity. So this is the only property required in case of my thermal calculations. Right. So this is required for my conduction. For my convection, I need to define that H separately as an input, or maybe separately during defining my boundary condition. Same is the case for radiation, right? So that is the basic difference between these two materials. So even if they are similar, then here we have the material properties, or I'll say different material properties my solver is using over here. Now I'll go to the design modeler. I will right click on geometry and just say design model, new design modeler. Okay. So here, before going into that, I just go to units and set it to millimeters, right? I just click on one of the plane so that I can import my external board geometry into that plane. I will go to today's assignment and just say piston. Okay, so I have imported the piston. I simply make it off and just like check the geometry. Sometimes, maybe here today we have some time. That's why I'm explaining this. Sometimes what happens, you see such edges in your model. So you can see this additional edge. Uh, it may not be present in your actual model or actual manufactured part, because this is error from my 3D modeling. So this edge. Correct. So, if you need to calculate like very precisely, what you can do, you can simply delete these edges here in design modeler. You can do that. Maybe I will show you. You have one option, just merge faces. So there is one option that you can use. So instead of edges, just select faces, and maybe you can select such faces which you need to maybe have do not have such edges in that, or maybe inside also I'm having some area I saw over here. So what I have done, so I have simply added the all the faces which I need to merge. So maybe somewhere here and this one. So if I just hit apply, so I will have all the faces, and that if I just say generate, you can see now I got the full face, and this will be in reality. So what if you see this piston, manufactured piston, it will not have such edges. So while modeling this part also you need to take care, means just to delete these edges at the end of your modeling, right? Okay, so this is just addition I have told you. So nothing related to our calculations. This you can do just to increase your accuracy of results, or maybe it may have like what I'll say. It has cleaned your geometry. That's why my now element size will be less, and maybe my solution time will be faster, little bit faster than the earlier one. So those are the advantages of doing this. In case of like big assemblies, I strongly suggest to do such geometry cleanup works. Now, just double click on the model section. So my mechanical is opening. Okay, now I'm into the mechanical window. So before going further, just check units. They're fine. Check the material. So it's by default a structural steel. Now I simply check my problem statement. I need to define global element size as 3 millimeters. So I just go on mesh, go into the sizing and element size. So I'll just say 3 millimeters. Uh, Now I have one question for you. So I just said global sizing of 3 millimeters, right? I need to define element size as 3 millimeters, that to global size. So can anybody tell me what is other technique to define this element size? Any other than this global sizing? So I already told this to you in, I guess, second session, means assignment number 3 is something like that. But in our second session I told you two ways to define your element size. One is global element size, and what is other one? I told you like you can define your element size by two ways, and in case of assemblies that is required. In case if you have more than one parts. Hmm? Can anybody tell me what is other sizing technique? So this is nothing but my global sizing. Okay, I'll tell. So I'll simply generate this first. Let's see. So all my body, it is meshed with 3 millimeter element. Now if I just right click on my mesh and say insert, and if I add maybe sizing, so this sizing, and wherever I'll be applying, maybe I can select some face, edge, or maybe vertex. Now I want to select this face, top face. So instead of 3 millimeters, what I will say over here, maybe 2 millimeters. So this 2 millimeter is nothing but my local sizing. So I have two different methods. One is local sizing and one is global sizing. So whatever I'm defining over here as a 3 millimeter, is my global size, which will is applicable for my whole body. And now only for this phase, I will be having maybe instead of two, I'll say one, just to have a clear difference. And I'll say generate mesh. So you can come to know. So can you see the difference? So this face is finely meshed and all other body is meshed with bigger element size, right? So this is global sizing and local sizing. Fine. So I will change it to maybe 2 millimeters because otherwise it will take a lot of time for solving. As I'm increasing my nodes or elements, my solution time it will increase. Now I'll simply check my boundary condition. Boundary condition is the temperature on this top face, and which is equal to 2000 degrees Celsius. Fine. So I'll simply right click over here, say insert, and you can see over here. So here no load is available, no pressure is available, no force is available. So here only terms available are related to my thermal. So temperature, convection, radiation, heat flow, or maybe perfect insulation, heat flux. So those terms I can add, right? So now I'm adding temperature. So I simply select this space and say apply, and here instead of 22 I simply say 2000 degrees Celsius, right? Now I will apply second boundary condition. What it is saying, convection on all faces except this top face where we have applied temperature, and with the convection coefficient of 0.2 watt per millimeter square degree Celsius. Okay, now what I'll do, I'll simply right click, say insert, and say convection. So what is my film coefficient in that? 0.2 watt per millimeter square degree Celsius. Now, I think now it is very big task to select all the faces, right? Means I need to select all the faces, this whole and all. Maybe I can simply go to this. Let's check it. Uh, am I going with the wrong way of selecting faces? So I must say no. So because this will take a lot of time for me to select the faces. So instead of it, what I will do, I will simply go to box select instead of single select. Just click over here and drag it. So all my faces will be selected. Now I just go to single select. Now I press Control key and just press on this top face. So now you see what happened. I have selected all the faces from this body and I just unselected the above one. Now I just go here, no selection, and say apply. Here on bottom you can see how many number of faces are selected. 35 faces are selected, and this is the area of selected faces. 35. I say apply. Got it. So instead of selecting it with like this single selection, so it's very much faster with this box selection. Fine. Now I have applied temperature, even I have applied convection, and I have defined my coefficient as 0.2 watt per millimeter square degree Celsius. Fine. So I simply go on to the problem and check. So yes, my like boundary conditions are defined. Two boundary conditions was there in as input. Now in output or in post processing, I will need to have temperature distribution and heat flux. Okay. So before that, I'll just solve this. Maybe I'll click over here and say solve. Okay. So my solution is done. So now I will right click and say in thermal temperature, or I'll simply click on this. I will have this menu visible. In temperature I'll select this one. By both way I can go. So even I can right click, insert thermal, and say directional heat flux. So I have applied temperature in this z axis. So I'm interested in z axis now. So I simply right click and say evaluate. Can you see? So this is my heat flux basically. So you can see I'm having minimum, and this side the red, you can say it is going from this to this side. uh, Temperature, so this is nothing but my temperature profile. Maybe I'll simply make my go to the view tab, windows, and say just reset my layout. You can see, so in my piston, so in reality, this 2000 degrees Celsius is there on my top face, and even it is traveling up to some extent. It is traveling from this to this point. So here also I will have a lot of temperature. Maybe I'll go to probe and just say. So can you see how my temperature is going down from top to bottom? Not bottom exactly, but from this top portion to this portion. This is nothing but my variation in temperature. And why it is happening? It is happening because of my convection, because continuously I am taking out heat. That's why my temperature is dropping. And at the bottom, if I can simply put one probe, you can see the temperature. Got it? So by this you can come why this is important while designing, because you come to know here, like, this much thickness, up to this much thickness, I'm having temperature above 100 degrees Celsius. So in that case you decide, like, what thickness you need to have for this. So I'll show you one more new thing today, maybe in temperature itself. Just I'll go to one plane view. I just selected this Z axis. There is one section plane available, so I can put a section plane, and I can simply just click it over here and maybe simply drag. I can see a cut view of my model. So that I think I haven't told you until now. So that's possible, and here you can see that section plane window. And you can add like a total six number of planes in one calculation. Maybe I'll simply click here or here again. I will have one more plane, so I can simply, can you see? So like this you can make. So this type of results you can showcase. Now I'll simply close this wireframe and just maybe I'll say no wireframe, so you can have such good results. What I will do now, I have these probes. I will delete all these probes just to have clarity. Now, so this is my thickness. So here I can put the probes. That's why it is very important to design this thickness. Means by these calculations you come to know how much thickness is really necessary, just to avoid, like, the temperature at bottom. uh, Means at bottom my requirement is I should have minimum temperature, minimum possible temperature. On top I'm having 2000, and at bottom my requirement is I should have minimum temperature. So by doing such like a variety of calculations, maybe in one calculation I will use maybe this much thickness, in other one I will try to reduce this thickness by maybe 5 millimeters, or maybe I will increase it in another calculation by 5 millimeters, and I will simply differentiate among them. So this we call it as nothing but optimization. So whatever material I'm having, I'm just checking by adding or reducing the material, and I'm checking what is the best suited solution. So this is nothing but optimization. That this you can do over here. So for that you need to run this model for multiple times, and you need to compare the results of all these uh, variants basically. Fine. So yes, we have calculated the temperature profile, and we also extracted results for heat flux in the direction of the z axis. Okay, so uh, I think our first problem for today is complete. I'll quickly move to the second problem. Okay, so here we have our second problem. Uh, this model again, it's I need to ask one question. So, what do you think these parts should be? So here, nothing is mentioned regarding the part name. That's why I'm asking. What do you think this part should be? Maybe I'll close all other tabs. So here it has. I have opened it. So have you ever seen such part somewhere, or maybe I'll give you some hint. Oh yes, perfect, perfect. This is nothing but disc brake of your maybe bike. So at front wheel, you must have seen such a part. So maybe with some like, so here holes are more in number, maybe with some less number of holes. But yes, this is a part of your bike, and it's a front disc brake. So yes, I'll read out now problem statement. What it is. Same thing again, we will be having a structural steel thermal category material. Now I have to define here element size, global element size as a 10 millimeters. Temperature for these phases. So here they are saying like temperature on outer two faces. These two basically means one from for up front and one from the back end. So I'm having a disc in between and I'm just pressing it from both the ends. So there I am having like a piston cylinder arrangement, and my piston is pressing these discs basically because of my hydraulic pressure. So that's why these two faces here we have mentioned. One is from this side and one is from back side. Convection on all faces. So except this one where we have the temperature. So all other faces should be with the convection, and that too with the convection coefficient of 0.2 watt per millimeter square degree Celsius. And here we need to get results for temperature distribution over the body, and heat flux. And in addition to that, I need to find out equivalent stress and total deformation also. Okay, so now in so these are my thermal results. And in addition to these results, I need to find out my structural results also. So equivalent stress and deformations are nothing but related to my structure. Fine. So now here I need to use again same thing what we did yesterday. For these results, I need to perform a steady state thermal calculations, and for this calculation or for this equivalent stress and total deformation calculation, I need to use a static structural analysis. Correct. So let's check. Let's see how we're gonna do that. Uh, Let us first pick the steady state thermal. Maybe after this one, I'll show you like there is also one shortcut to do this. Maybe after completing this, if I forget, just uh, interrupt me and ask me. You said that you will be saying us one shortcut for this one. I'll tell you, but after completing this one, so regular way. So here in engineering data, the default material is static structural. Let's go on to the geometry, right click on and say just new design modeler. There, I'll simply pick units as millimeters. I'll click on one of the plane just to import the body, and I'll say import external geometry, and that is nothing but my disc brake. I'll say open. Now I am going to say generate. So yes, here I am having my 3D model. So again, I'm having, some edges. So unnecessary edges. So this is unnecessary one. So these are unnecessary edges. I can remove those edges here in Design Modeler. And this process of removing such extra edges which are there because of bad modeling. This process is called geometry cleaning or geometry cleanup. Fine. Just keep this word in your mind, geometry cleanup. Just it is a process of making your model like a dirty model to clean model. Dirty model means not like it had some dust. Dirty model means it has some edges or some vertices or maybe unnecessary portion, maybe this one. So this is unnecessary one and this will not be present in reality. So such model I can say as a dirty model, or maybe some model with some additional holes, something like that, so which is not needed in your calculation. So those parts you can delete it in this design modeler itself. Fine. So I have defined the geometry. Now I'll simply click on the model so that I can enter into the mechanical window. Let's wait. Okay, so here I am into the mechanical. Now simply check units, set to right units, check the material. It's fine. Now I need to define the element size as 10 millimeters in global. So I'll say right click and click as generate. Okay, so my disc brake is meshed. Now here I will apply boundary condition. So I'll simply right click and say insert and say temperatures. So for temperatures, uh, I saw like I need to have temperature on two faces, that to 200 degrees Celsius. So this is one face and the other is from back side. So this one. So this face basically is compressed and my brake is applied, right? So because of my friction, my temperature is generated. So what temperature is 200 degrees Celsius. Fine. Now I have to select all other faces than this for my convection. So what I will do, I will go to the box selection. I will select whole part. Now I again go back to single select. I press Control and I simply select these two faces which I want to exclude from this. Right, so all other faces are selected. Just check over here, they are 191 faces. If I wanted to select them by like single click, then how tedious job it would be. But with this box selection it has become very easier for me. I'll go to insert and say convection. I need to define film coefficient as 0.2. Fine. So I have defined two boundary conditions and that's it. So I'm done with the my boundary conditions. So I simply say solution and say solve. For that I go to view windows and say reset layout. Now I will add results for my temperature, and again I will also add results for my heat flux or maybe directional heat flux, and just say Z. So it might be anybody. If you are interested in X, you can find out results for X direction. So you can see. So this is my heat flux results. This is my temperature results. So I just want to point here. I am having 200 degrees Celsius. As I go from outer side to inner one, my temperature yes is goes on reducing. Fine. So can you see? So this is important one. Just to design or maybe just to say what thickness will be required to sustain this temperature. You can find out from this region. So at middle exactly, you have a temperature below 50 degrees Celsius. Fine. Now my first part is complete. I have results for temperature distribution and heat flux. Now I need to calculate equivalent stresses and total deformations. But for that, I need to add one more calculations for static structural. So what I do, I just drag the static structure portion and drop it onto row number 6, which is my solution. Because whatever results I will get, for that I need to use this results or this thermal solution as an input. Basically, I will tell you over here, so that will be more clear. So maybe I'll go here and check. So imported body temperatures. So whatever these temperatures we saw over here, they will be used as an input in my structural calculation. Got my point? So same thing like our yesterday's pre-stress calculation. There, what I was doing my model calculations, but with results of my earlier static structural calculations. In that, I had some loads. Due to that load, some stresses were generated in my model. So that stressed model I was used for calculating my natural frequency. Same thing. So my body over here is already subjected to some thermal loads, and with that thermal loads, now I need to find out the structural stresses. What structural stresses are coming into it, or what deformations are there in my body, that I need to check. So I can do in this way. Now what I will do, I'll simply right click over here and say import load. Otherwise, I'll skip this and maybe I'll simply go and maybe fix one point. So I'll just fix the holes, maybe bolt holes I'm having over here. Here also, I'll take help of pop selection because I'm having multiple edges there. I'll simply select the inner faces of this hole. Okay, selected. So that portion I have just fixed out. So I have applied fixed boundary condition, and simply what I will do, I'll right click and say solve. So done. So my structural calculation is complete. Now I simply insert here my stresses, equivalent stresses, and my deformation. Maybe I will use total deformation over here. I'll say right click and say evaluate. So see my deformation. So I haven't applied any external load on this. You note it, like here I do not have any force, any pressure, nothing. I do not have anything over here. But still I am having the deformation. Why? Because of my temperature difference. Because of temperature only, this 200 degrees Celsius, my this body, it's deforming because of my thermal expansion, coefficient of thermal expansion. Got my point? Even the stresses. So these are the stresses present over here, and you can see. So this portion is little bit highly stressed, so rather than this inner one or outer one. Maybe I can see this one. Let's just say undeformed. So here you can see it with a better view. Right. So what we did, we first calculated my disk break with some temperature and defining convection on it. I found out results of temperature. Then I used the same thermal model with the temperature in it, or maybe a thermal load in it. And with that thermal load, I checked the stresses and deformation in that body. Fine. So, okay, now I think we are done with this problem. But as I told you, I'll share with you one shortcut for this. So here actually, maybe I'll simply minimize this analysis systems tab. So below you have these custom systems, right? Like a third tab from this, you have custom systems. So there you have one option as thermal stress. Means thermal means steady state thermal, and stress means static structural. If you simply double click on this, see what you get over here. So no need to drag and drop and all do all these things. You can get simply the readily available model. So it is already predefined over here in the custom system. So here simply you can import geometry, you can define your boundary condition and say solve. And same thing you can define maybe any fixed support or any boundary condition in static structure. And directly you can say solve. So no need to have a separate drag and drop. Again, same things you need to do. Right. Now I'll delete this. So same thing you can do for our yesterday's problems also, like pre-stress model. So this is nothing but my model calculation. So maybe here you can see static, structural, and model. So these are predefined in Ansys, so you can use them. For time being, I'll delete them. So to delete it, just click on the arrow and say delete. Fine. So I'll save this, and now I just want to move forward to the next calculation. Let's see what we have over here. So I think this body is not clearly visible, but yeah, I can tell this is kind of maybe heat sink. Maybe you have some PCBs. So there you might have found such heat sink using such sink over there. Here I'm having temperature as 230 degrees Celsius on all the fins. My all bottom faces means basically one face only. So uh, okay, so this is the source of temperature. Sorry for my earlier words. My temperature will be from my bottom part, and these fins are for my heat dissipation. So my bottom part is with temperature 230 degrees Celsius, and again I am having the like default material, default element, and here I am having convection. But here I do not have. Just a minute. Yeah, here I do not have the value for my film coefficient or coefficient of heat transfer. Instead of that, I'm having a model. Use available temperature dependent data for stagnant air and vertical planes. So these are nothing but my standard models, and these all models like stagnant air, vertical planes, horizontal planes, or moving air. So all these models are available in my Ansys library. So let's see how we can make use of that models. So just go to the project window, go into analysis systems and say steady state thermal. Just double click on this. You will get this one. Just double click on this and just say problem number 3. So as we have default material, I will not going to touch engineering data. I simply open design modeler. Okay, my first part always should be to check units. Just shift it to millimeter instead of meter. Select the plane. I have selected it. Now just go into the file and say import external geometry. This is nothing but my heat sink. Okay, so I'll say generate. Perfect. So this type of heat sink I'm having. So mainly just to dissipate heat. from my PCBs. Such type of heat sinks are used. You would have seen some IC boards or something like that. So there you must have seen such heat sinks. So these are basically to dissipate heat. Maybe my source of heat is somewhere here, and they are just transmitting my heat to the air, and they are dissipating. Fine. So I'll go to the model. I'll double click on the model part and just wait for mechanical window to open. Here it is. Just check with the units whether they are in millimeters. Fine, it is. Just check the geometry. Structural steel material as a default one. That's fine. So maybe I'll simply click because it's a default mesh. It has Yes, very nice mesh. So can you see the difference in mesh over here? Whatever earlier mesh we had, those were having some tetrahedron shape elements or element. But here we have exactly like brick shape element. So we call it as a brick element or maybe a chord element. So both are the same for same element. So either you can call it as brick element or a chord element. And here in bottom you can see again I am having a similar kind of thing, a prism kind of elements are there. Okay, so just go to the temperature. It's 230 degrees Celsius. Simply right click here and say insert temperature. So from the bottom place. Okay, so I have selected the bottom face for temperature. Now all other faces I need to select except this one. So what I will do, I'll go to box select, say like this, and again I go to single select and simply press this face. So just one select this, and I just check number of faces selected, 129 faces, and add a convection. Fine. So until this, you know pretty well like how we're gonna do. But here now I do not have the value for this film coefficient. But instead of that, I'm having which model to be used. So stagnant air with vertical planes. So this model I need to use. So what I will do over here. So here you can see one arrow. So in this film coefficient row, here you can see one arrow. So I'll just click over here and maybe I will go to the import temperature dependent. So here I'll go import convection data, right? Maybe I'll repeat this. So here in film coefficient, if I'm not having any value for this film coefficient, then what I will do, I'll simply click on this arrow, and from this menu I select import temperature dependent data. So I'll say import convection data. So all these convection samples, they are inbuilt with my Ansys. And which was my model? So it was stagnant air with vertical plane. So I'll select any, maybe this one. So this is plane 1, plane 2. So stagnant air with vertical planes, and I'll say okay. Fine. Here you can see coefficient type, average film temperature. As you select the convection, you can see this convection coefficient. And this is in graphical form, and here you can see a tabular form. So I'll simply drag it somewhere to this side. So this is nothing but temperature dependent data. So this is my convection coefficient, nothing but my film coefficient over here. So this value is changing according to my temperature. So if I'm having 1 degree, then I'm having this much coefficient. If I'm having 1000, then this much. And you can see those values over here plotted in the form of my graph, right? So instead of a single constant value, I'm having over here a tabular values, right, for different temperatures. Okay, so I have defined the temperature, even I have defined the convection also. Now my part of defining boundary conditions is complete. Just check the output. So here you missed, but yeah, we will check the temperature and flux. Before that, I'll simply hit solve. Just right click and say solve. Okay. Right click and say insert in thermal and just temperature, and maybe right click and say uh, heat flux. So in the direction of Y. Nice. You can see the heat flux value changing from this bottom end to the top of this fins, and the temperature. Can you guess what happened over here? Why I am not seeing the temperature? Can anybody guess what would have happened over here? Why everything is blue and why I'm not seeing any color? Hmm? Can anybody guess what would have happened over here? So why everything is in blue? What part we missed? I'll tell you. So while defining the temperature, I haven't entered the magnitude. So that's why it took by default as a surrounding temperature 22 degrees Celsius. So, but instead of that, I want to have it to 30 degrees Celsius that we haven't entered earlier. That's why I got that blue color everywhere. So no temperature difference basically. Okay, fine. Now I got the exact results. So see, so how it is behaving. So let me just make it visible in the x-axis direction. Fine. Just make so if I am having a heat sink and my heat source is somewhere over here, so you can see how it is behaving. So these fins at top, they are nearly at like minimum temperature. This one, maybe I'll put some probes also over here. So almost I can say around 35 degrees Celsius drop in the temperature because of these heat sinks. Correct. So yes, while designing such heat sinks, you can take help of these calculation results. So you can decide here like what amount of thickness is necessary, uh, how many numbers are fins are required. So those trials you can perform over here, and you can decide like what is the optimized design for you, or which design gives you good results, like in terms of number of fins, in terms of thickness of films, or even height or width. So anything, so you can play with a number of variables over here, right? For only to do that, you need to perform like that number of calculations, and you need to compare its results to get optimized solution. Okay, I think we completed this problem also. Okay, so we have I think four. So this is the last problem, I guess, for today. Here we have the engine block, maybe of bicycle, I guess. Bike. Sorry, not bicycle. For one of the bike, and temperature in the cylinder bore is around 600 degrees Celsius. Again, convection for all the outer surfaces. Again, same available temperature dependent data we need to use for stagnant air, and that too a simplified case. So this data we need to use. So now I want somebody from you just to be with me, or to tell me like the steps which I need to follow. So maybe somebody from voluntarily someone can unmute himself or herself and just join me and tell me like the steps to be done. So uh, So this is helpful for you because if you understood everything, you will tell me exactly correct steps. And if you missed something, maybe like during when you are telling me the steps, if you miss something, maybe I will point it out, and maybe it will be very clear to you, and maybe you will not forget that afterwards. So this is important for you only. So just voluntarily unmute yourself, and you can say me like I'll tell. So this is the problem statement I already told you. So we need to solve this. So can anybody guide me now? Anyone? So we are nine in numbers. So can anyone? Hmm? Will you? I think you are the most or attentive guy from my first session, I guess. So will you guide me for this fourth problem for today? Unfortunately, I can't see your name, but yeah, you can see it over here. I have tagged you. Hmm? Okay, I'll start midway. If you join us back again, you can just be with us. Meanwhile, I'll start. Uh, I'll simply drag the steady state thermal assessment. So here I just check on the material. Okay, so nothing related to material they have said. So I'll simply use the same default material. Now I'll just right click on geometry and say new design modeler geometry. And yes, so my design modeler is open, that window is open. Just go on to the units and set it to the millimeters. Just hit on one of the plane just to import my external file on that plane. So just go on to files and say import external body. There I need to select the engine block. So okay, I just press it and say generate. So I have this engine block. Just go into the view tab and press untick this frozen view. So yes, I'm having this engine block. So now my aim is to apply pressure on this face, basically inner face. So here actually my piston will be moving like to and fro motion will be there for this piston. And because of that some temperature is generating because of the compression of my fuel, or maybe all the strokes, compression expansion strokes. So that temperature I will apply over here, and all other uh, portions like this external faces, here I will apply convection. Fine, so I'll go to the model. Let's see. Okay, so I have this model open. I simply check the material. So it's default. I check the units. It's fine, millimeters. Now I simply right click and say mesh. So let's see how my mesh is generating. I think this is little bit coarse mesh. Maybe if I can just check it, so can do maybe put 5 millimeters. Okay, this seems a little good one. Now I have to define the temperature from inner face. Let's just right click here and say temperature. So I add temperature on this inner face. So I have selected this with a single select. I have added it. Just know the value as 600 degrees Celsius. Magnitude is 10. Current faces. Fine. Now I have to apply the connection. So I can do by using box select like this, and I simply untick, or I simply unselect the faces from inner cylinder. So this one, these are unselected. Maybe I'll just go back and just for check. Here you can see my total faces, selected faces are 244. Now I have to unselect 2, means it should remain 242. So that's fine, I'm correct. So I simply right click and say convection. So all the faces are added. Now I'll simply check which model I have to use from the available one, stagnant air and simplified case. So what I will do over here in film coefficient, I'll click somewhere over here, then this arrow will appear for me. I'll click on this arrow and say import temperature dependent data. So this is import convection data. So there I need to use this data. So this sample basically. So stagnant, uh, this one, stagnant air and simplified case. So this is stagnant water. So I do not want to use stagnant water. I want to use stagnant air in simplified case. Okay. So I simply hit OK afterwards. So it has taken this one, and here you can see last time when I took the other sample, so there it was having some graphical data, but here you can see I have only one data. So at 21 degrees Celsius I am having this much coefficient, convection coefficient. So this is possible, right? So this is nothing but my a simplified sample. So I think I'm done with definition of my boundary conditions. Now I'll simply right click over here and say sort. Okay, my solve is complete now. Say insert and say temperature. Say insert and say directional heat flux. Now I can say y-axis. Just say evaluate. You can see the heat flux changing and the temperature. So whatever coming around this cylinder is in red. So that's around 600 degrees Celsius. Just check with the probe, and whatever like away from my cylinder. So yes. So this is the difference in the temperature as it is as we are moving out from my central cylinder. Right. So yes, I think we have completed the assignment number 6 today. So do anybody have any question? If you have extra 5 minutes for the your question and answers. Do we have any question? So meanwhile, I will simply check what we have for tomorrow. And yes, I think tomorrow is Saturday, and tomorrow our session will be in the morning. So yes, tomorrow we will be having transient calculations. So transient means we will have again time dependent loading data basically. So maybe in this like in our today's calculations, what we checked the temperature as 2000 degrees Celsius in a single step. But tomorrow what we will be going to see, if I'm having like a rise in temperature like starting from 0 to 2000, so how my body will be behaving. So tomorrow's session also will be a good one in terms of uh, thermal calculations. So tomorrow we'll be seeing all the transient analysis. Okay. So do we have any questions? Okay, fine. If not, then I think yes, I'm done for today's session. Uh, I think those who do not have any questions, they can leave for the session. Those, if they have, then they can ask me, or otherwise we can stop here. Okay, then fine. I guess nobody has any question. So see you tomorrow morning, and have a good night.
Good night.
Okay, bye bye.
Thank you, sir.
Welcome. Bye.